Thank you, everyone. I'm happy to give this presentation because we just published a document produced under the last term of the Service Life Prediction Committee 365. The document was just published like 2 weeks ago. It's available on the ACI website for anyone who's interested. This is the cover page, and I'm gonna go through what it is, why we selected a rather different type of document compared to a code or a specification, and the reasoning behind those decisions. It took us 7 years to get this document through the motions of committee consensus, TAC. It got 3R, like form work. So we've been through the paces, and now we are very happy to have it available to the public. Why we do this? We understand that we are currently in our society, there's pressing needs for being or having resilient and sustainable construction. We have realized that our resources are not infinite, and more importantly, that fixing structures costs money and time. And overall, we have to understand that the best way we can do this is if we have put some thought into how we're building things, how we are specifying it, and have engineering judgment behind decisions that are made during the design process. So why a design specification compared to a code or a construction specification? A design specification is a type of document that would fall on, this is from the TCI, ACI, Technical Committee Manual. A design specification is a rather special type of document that falls under the category of codes, but unlike codes, it does not have to be adopted by building officials. What does this mean? It means that it only becomes part of the construction document when an owner requires it. This allows the specification to be used in projects that are important, like a bridge or a tunnel, or a structure like a library, a hospital, etc., without having to put unnecessary burden on, let's say, lower impact projects like sidewalks or residential construction. Because otherwise the requirements of doing a whole service life prediction would be too much for the scale of the project. So this is the main reason why we do this. And like I said, it's written in mandatory language, just like a code, but it only becomes active part of the construction documents when the owner has has made a decision that they want to have a structure that is going to be designed and constructed to last a specified number of years. Here's a summary. There are other design specifications within ACI. Like I said, they're not as frequent as codes and construction specifications, like 318 or 301, but for this type of special type of projects, they are available, and they could be the right solution for each application. Again, maybe from some of you that have heard the term service life, but sometimes it's very common to have misconceptions about what that means. In the simplest term, a service life of a structure is the estimation of the time under which the structure will have a specific performance. The difference between service life and other limit states is that when a structure reaches its service life or the end of its service life, it doesn't mean that the structure is about to collapse. It just means that we have achieved a condition that requires us to do something. In practical terms, this means we need to spend money to fix it somehow. And the reasons why we need to fix it, or the way we need to fix it, can vary. Also, such as the scope and the amount of effort that needs to be put to do that. So it's not the end of use, and it just means that we need to implement resources. So in this circle, this is a simplified closed construction schematic of how we can build things. The service life design or prediction of a structure starts with the planning, with the basic design of a structure. and continues all the way until the structure is deemed unserviceable, or we have achieved a point where the structure is too expensive to repair and needs to be replaced, or we just continue to implement maintenance and rehabilitation strategies to keep pushing the end of the service life of the structure. So in simple terms, we have ultimate limit state. We're never going to be working in that condition when we're doing service life. We're always going to be well below that. So over time, we have a structure where on the vertical axis is going to be how deteriorated it is. For many years, it's going to be working just fine. And then we start to see problems. And then the definition of service life can vary from project to project. In most cases, people would say, well, we have reached a point where the structure needs to have some repairs. If that is the definition that the contract documents establish, that could be the end of service life. But there are obviously the opportunity to do something, improve the condition of the structure in some way, and then again have it deteriorate in the way it's going to deteriorate for the specific exposure conditions until we decide to either do something or just stop with the project and perhaps think of something different. This happens a lot with bridges when they are replaced for wider bridges or different types of structures. The design specification was developed to be applicable to practically any concrete project that requires special considerations for service life, from bridges, infrastructure, tunnels, bridges, etc., transportation, you name it. The most important thing is that in this document, we very early realized that we cannot address all scenarios, and we simplify things by just focusing on new construction, where the service life engineer, which is a term I'll define in a minute, has the ability to make decisions from the very beginning compared to dealing with an existing structure that already has problems, and the opportunity or the challenges to make decisions to extend that service life can be limited. It requires the service life engineer to come up with the basis of design and the end of service criteria, as long as minimum requirements for how you're going to do or achieve that service life. It does not require the service life engineer to follow a particular methodology, because there are different ways where it can be achieved, just like codes and other documents do not tell the licensed design professional exactly how to do their analysis, structural analysis, or the construction sequencing, etc. So service life engineer, this is perhaps the most important and often discussed part of the design specification. Who is that person or that individual? Is anyone who is a licensed engineer in the jurisdiction where the project is being executed. That's a very important part, because it comes back to responsibility. And that individual has to have the competency to be able to discern what are the critical exposure conditions that can reduce the service life of the structure, and it has to be cognizant of what are the means and methods that can be used to resist that degradation and extend the service life of the structure overall. This roadmap gives you a breakdown of the sections of the specification in a simplified way. It follows a logic pattern where we start with, okay, what did the owner want? Once we understand and have an agreement of what they're looking for, we're going to have a basis of design, and then we're going to do an analysis for the cases where we have enough information and know how things work to make a prediction. And for the cases where we don't have a robust understanding of the problem, we can use deemed to satisfy approach to say, well, we're not going to use a reactive aggregate because I don't want to deal with modeling ASR, which is really complicated. Ultimately, projects on this, like say, bird's view level look very simple, but as we will discuss later, in reality, things start to get messy when the construction begins, and there's going to be some iterations of the analysis based on what is actually happening at the construction site. The end of the specification comes with a service life report, and I think someone mentioned the birth certificate during the earlier presentations today. This is the same thing. We're going to have a record of what was actually the design or the plan and how it's executed. It's like watching film after an NFL game. You want to know what went wrong and what went well, and then we have a structure that is commissioned and starts to be serviceable, and then we'll have some. We're going to go back to it at some point at the discretion of service life engineer to look at it and see if the prediction is working well. One of the most important, or perhaps the most important aspect of this is we need to have a clear understanding of what we mean when we say service life. For an owner, it can be, okay, I don't want to have to do anything. And for other owner, it can mean, well, I'm going to be having maintenance and monitoring crews every 5 to 10 years, and then we'll until we achieve the required service life. And that is a big difference. If, for example, if I want to have a vehicle that can be guaranteed to have 100,000 miles without a single oil change, it's most likely not going to look like a car I can get from a dealer. It's going to look like a tank. And more importantly, I'm as the owner, I'm taking the decision that I need to understand that it's not going to cost me the same as my Prius, right? It's going to cost me 5, 10 times more just because I'm prescribing a level of detail and reducing my tolerances in such a way so that I can achieve the service life that I'm looking for. So one of the big, in my professional experience, one of the biggest pitfalls of service life prediction is that owners have a structure, and then after several years, they start to see problems, and they look at it and say, well, this was built 10, 15 years ago, or 20 years ago. What's going on? And the fact is that they never planned for having something that would last more than that under those specific conditions. Parking garages is a good example for that because they're built everywhere in the country, and the exposure conditions in Florida are going to be different than in Minnesota. And if you're like a company that manages this type of properties, you're not going to have a good understanding of why these parking garages, even if the signs are similar, they are behaving the same way. So it's very important to have this discussion up front so that we can have or avoid this type of situation where I want something, I don't know what I want, I'm telling the engineer, get me this. They kind of understand what the owner wants. They put a set of drawings and specifications. The contractor built it the way they could. And ultimately, we don't get what we were looking for from the beginning. And this is something that we have been battling in the service life community for a long time. And the main focus of the specification is to make sure that this is not happening going forward. The model selection, get a lot of questions about what is the ACI required model for service life prediction. And the reality is that we don't have a single one. There are several approaches out there. Some used in a more academic setting. Some are used in a more practical engineering approaches. Those are okay. And it's the responsibility of the service life engineer to understand if I have a specific condition, a simple model can be, a simple equation can be just what I need. When it starts to become more complex and I have varying exposure conditions, or I'm dealing with aggressive environment, then I probably should be aware that maybe I need to do something a little bit more robust to make sure that I'm getting a good design for my structure. Currently, we only have good tools to model corrosion, chloride ingress from de-icing salts or marine environment. This is perhaps over the 25 years where service life prediction efforts have been made, probably 90% of the work has been done on corrosion. And it makes sense because it's the most common deterioration mechanism. But for other, like I mentioned already, ASR and similar, we don't have good understanding. We don't have a lot of field cases that we can extract information from, because once we have that type of problem, the decisions are typically made to replace the structure to avoid safety issues and whatnot. So we don't have enough a robust body of knowledge to make predictions for some mechanism, the regulation mechanisms. And we also need to understand that things vary in real life. We cannot, if we have a project where we're trying to achieve 75 years from, let's say, 2025 until 2100, how is the world going to look like? We're constantly listening to climate change. How are structures going to be designed, for example, near coastal areas where the frequency of hurricanes is starting to increase? So there are a lot of uncertainties in the way the world will look like in the next decades. So we have to account for variability in that design, and the design specification provides requirements on how to do that, and also provides requirements on how the service life engineer has to explain their thinking in a clear and concise way, so that once we look back into these structures, there is a logic description of the work that was done, and we can look back and say, okay, maybe this was a conservative assumption, or too conservative of an assumption, or perhaps it was not conservative enough. So we are kind of going to be learning from what we're doing so far in the coming years and decades, but we need to start with making a good documentation process so that we can actually learn from what's going on. I'm going to go through this quick, because I don't want to go over. But one of the important things is that it provides requirements of, okay, once you have a design, how you're going to validate that. And that, for a construction project, means testing. Again, owners will not like that, because that is an added cost. But if you're looking for something that is justifiably important for you and you want to achieve a long service life, you have to understand that we need to make sure that every single portion of the structure is built with the materials that it needs. Not only from the design process, but also during construction. And this is where things can start to get a little bit sketchy. And we need to have ways to go back and say the actual structure that is built is reasonably in accordance with the design plans. And we go through a lot of situations where something obviously goes wrong because the world is imperfect. And how do these type of situations affect my analysis? We have to make sure that there is a connection between what's happening behind a computer screen and what is actually happening in a construction site. So the design specification addresses that. And going back to the roadmap, in reality, this is looking like this. There's a moving process and a moving in a project where things continue to change as the project develops, and what was initially envisioned may have changed over the course of the project. And then once we have the service life report, we need to make sure that whatever is actually built is recorded so that we can have a completed project, even if it's, slightly different than the original design. Key takeaways: this document is not going to solve all the problems. It doesn't address existing structures. That's going to be the next document that we're going to start working on. It just provides the framework for establishing basically guardrails on how we can do this as an industry, so that the analysis and the reporting structure for projects that do require a specific service life is relatively consistent among practitioners going forward.